Hello everyone, this is Professor Keen. Today we'll be talking about Chapter 2 in a student's guide through the great physics texts. The chapter is titled The Life and Death of a Magnet. The first question that we want to address, and this is by way of review from the previous chapter, let's suppose we have a rod of iron and we rub it with a magnet. One end of it becomes north and the other end becomes south. Okay, so remember what happens when iron is rubbed with a lodestone or some other, I'll just use the term magnet, with another magnet. Well, remember the idea is that let's suppose we have a magnet. I'll draw a bar magnet to make it a little bit more obvious what's going on. So we have a bar magnet. I'm going to imagine that one end of the bar magnet is north. I am marking the north end red, and remember how we calibrated this as we see which end of it moves toward the Earth's north pole. That's the one that would be the south pole of this magnet, and so we'll mark the other end as north, right? And let's suppose we take a rod of iron and we rub one end of this iron rod, and this is the magnet. We rub one end of the iron rod with the north end of this. That end of the iron rod becomes south, and the other end of the iron rod acquires a north polarity, or north verticity, as he would say. Okay, so that's just by way of reminder. Okay, but what happens if you rub a stranger shape? This is a topic that Galileo talks about in the next on the next page, his chapter 5. This is on page 20. So on page 20, what if an odd shape like a ring of iron, a ring of iron is rubbed with a magnet? What happens then? So I'll once again draw this magnet. And now we'll draw a ring. Imagine a ring of iron. Like this. And this end is north. Like that. And you rub it. What happens? Well, he mentions that the other end of the ring becomes north. So this end of the ring becomes north, which is kind of what you'd expect, but it just maybe is a little bit counterintuitive. So you get this end becoming north and this end becoming south. So you still have an equator, so to speak. So if we drew a plane that cuts this, that would be the equator. Just like here, if we cut this bar like this, that would be the equator right there. Okay? All right. Now here's a more interesting question. What then happens if you split this ring right here? What happens if the ring is split? So if you took this ring that has been magnetized and you cut it right here, what would happen to this ring? Well, if you cut it there and you unwind it, what Gilbert argues is that you will then have a bar that has north poles on each end. So you split it and you unwrap it. Then you have, just like you had a north pole right there, and now you have both of these ends of this bar being north, and the south is going to be somewhere over here. Just like the southness was over here, the south is kind of in the middle. So maybe this is a little bit counterintuitive to you. You get two north ends of the bar, and south is in the middle. And maybe you're okay with this, but maybe this is a bit surprising to you because you think of bar magnets as simply having one end north and one end south always, but this is not always the case. Okay. This also, you can imagine forming something like this if you straighten this out. If you originally took two bar magnets that had a north end and a south end, so suppose you were to take two bar magnets and you were to put them south to south and then glue them together with strong enough glue that it overcomes the repulsion, right? So if you were to take two of these and you join them at the south poles, then once again you have something kind of like that. So this is conceivable. This is something one can do. Okay, let's ask another question. What happens when you cut a bar magnet? When you cut a bar magnet. Okay, so you have one of these bar magnets like this, or maybe a piece of iron that has been magnetized, and you were to cut it right down the middle and actually separate the pieces. What happens then? Well, it's not like, as you might imagine, you can have a north end on one bar magnet and a south end on the other bar magnet. Gilbert points out that this is not what happens. Whenever you cut a bar magnet, you acquire two new bar magnets, each of which has a north end and a south end. Okay, so if you want to think about, so this is the north end of this one, this is the south end of this one, this is the north end of this one, this is the south end of this one. In other words, you can't just separate off the north and south and hold them in separate hands. So you get, here's the answer, you get a new north and south pole. Right, here's your new north pole and here's your new south pole right there. You cannot simply separate off the North Pole or the South Pole all by itself. And we're going to find that this is different than the case of electrical charges. So you can take a positive charge and have it all by itself and hold a positively charged object in your right hand. You cannot be holding a North Pole object in your right hand. There's no such thing as a magnetic monopole. They always come in pairs. So this is unlike electrical charges. So there's a fundamental difference between electrical objects and magnetic objects. Electrical charges, you can take a positively charged object and just hold it in your hand all by itself. And you can take a negatively charged object and hold it all by itself. But there's no such thing as just a North Pole that you can just hold there all by itself. You've always got these pairs, north and south, like this. That's going to be an important point. We'll come back to it later. Okay, what happens then if you try to bring these separated parts back together? Or what happens if you bring these back near each other? The separated halves back near each other. Well, as Gilbert mentions, when you bring them back near each other, the north and south attract, and so they're going to want to snap back together like this. So you've got right here the North Pole here, the North Pole here, and these two kind of snap back together. But if you bring them back together in a different way, kind of side by side, then they are going to reorient themselves. And he touched on this in the last chapter as well. So if you take them, kind of put them side by side, they are going to approach each other, and one of them will swing around so that they snap back together like this with opposite poles near each other. So you have the north here and the north here, because this north wants to be by a south, and this north wants to be by a south. So it'll snap back together like this. Okay. How does Gilbert understand this? Gilbert uses an analogy, and I don't know if this kind of thing does anything for you, but let me just show you how he's thinking about this. He's thinking about this similarly to the grafting of plants. So if you look at the next page, he mentions that if you cut a tree or a branch in half, so he shows a branch here in figure 2.2, you cut it at point CD. If you try to graft it back together at this point, it will graft nicely. If, however, you flip one of these around so that you try to attach A to D and graft it together, it will not grow. He says here, the extremity CD, if skillfully grafted again on D, begins to grow just as B and A, when united, become consolidated and germinate. But if D is grafted in A or C on B, they are at variance and grow not at all, but one of them dies because of the preposterous and unsuitable opposition, the vegetative force. There you have this notion of a vegetative soul, which tends in a fixed direction, being now forced into a contrary one. Now, of course, this isn't the same as a magnet, but the idea he has is there are certain ways that nature behaves that if you try to violate that, it will not work. Okay, so why don't we stop there, and we'll pick up this discussion next time.